Good morning to all the participants. Today, we are going to have an expert talk by Professor Satish Kumar Sharma, sir. He is having a vast experience in the field of microchip antenna. He is also working on international projects, and he is also concerned with the various international projects in around the world. And today he is also going to talk about the for the further studies about. I would like to request her to please have a talk on the for the further studies in the foreign countries such as postdocs and the PhD also. There's yesterday there was a lots of questions that was arising about the filtering antenna also, sir, and uh, I told them that they must have a discussion with you at the last of the session. Then sir has done his PhD from IIT BHU and Banaras Hindu University. Then sir has done his BTech from the KIT Sultanpur, and his IIT is from then his area of interest is research and development of millimeter wave antennas, active phase array antennas, massive MIMO antennas. He's also related with the 5G communications related antennas, and for IoTs also. He is also handling GPS, GNSS handle and portable devices also. He's also working on a reconfigurable antennas and frequency agile antennas, null steering antennas, feeds for reflector antennas, and has got wide research papers and journals published in the major journals. He's also having a transactions also in a very reputed journals. Sir, I would like to request you to please continue your expert talk, sir.
Okay, thank you very much. Well, I think I don't know what kind of audience you have here, but I
So
will
still the
start my talk.
participants are coming, sir. We will
So
keep on adding them, sir.
let me share my slide first. See if you see my slide first, then we can start the talk.
Yes. Yesterday, I was having a lots of questions, sir, on the WhatsApp
Mm-hmm,
about the microchip antennas, filtering antennas. Also,
mm-hmm,
they were asking about the filter also. That
mm-hmm.
lots of question was there, sir.
Yeah,
Even
I
there was
think
lots of questions from the participants that they want to go ahead with the further studies in the foreign countries, how they are going to approach them. They were asking for that also, sir.
do you see my slides?
No, sir, not yet, sir.
So let me first set up those, and then I will talk to you. Okay.
Yes, sir.
I think since this is Google Meet is something I don't use, I use Microsoft Teams and Zoom. So this is
Yes.
something new for me. I think how to access my presentation is already open here, but when I'm sharing, it's not showing up. So there should be something called share right here.
Yes, share screen, sir. That is a
Yeah, I think I did that, but it's not sharing my, you know, my screen. So what it is doing, maybe I can stop share and share back. Something is not showing my screen to you, and I have already shared it. You do not see my screen?
no, sir. You have still not shared your screen, sir.
Well, it shows from my side. So I don't know, let me cancel and again restart that process.
Yes, sir.
So hopefully that will take care of it. Uh, does it show my screen yet right now or still not showing?
Maybe there must be delay, sir.
Do you see my presentation?
Yes, sir. Now, yes, sir. Now you have just now shared, but yes, sir. It is visible now, sir.
Okay. So do you see my title
Still,
slide?
Sir, sir, I would like to request Dr. Srikanth sir to please have a brief introduction about you, sir. Please, sir. Dr. Srikanth sir, please.
Thank you, sir. A very pleasant morning to one and all present over here. I, Dr. Shrikant Tiwari, Associate Professor, Department of Computer Science and Engineering, Institute of Engineering and Rural Technology, Prayagraj, Uttar Pradesh, India. On behalf of the Organizing Committee of Faculty Development Program and the collective of the Institute of Engineering and Rural Technology, Prayagraj, Uttar Pradesh, and on my own behalf, in today for first session, I would like to welcome our distinguished speaker, Professor Satish Kumar Sharma, sir, Department of Electronics Engineering, San Diego State University, USA, for this talk. Professor Satish Kumar Sharma completed his BTech in Electronics Engineering from KNIT Sultanpur, Abad University, now AKTU, India, in year 1991, and PhD in Electronics Engineering, Indian Institute of Technology, Banaras Hindu University, India, in year 1997. Professor Sharma also did postdoctorate from University of Manitoba, Canada, in year 2001 on antenna research. He has completed more than 20 sponsored projects from different funding agencies, including Aerial Antenna for Torpor, Scatter Communication, Flat Panel Phased Array Antenna with two stimulus scrabble beams utilize 5G, K-hand silicons, RFICs, and many more. He has published more than 88 research papers in different reputed journals. He has also published more than 188 conference paper in different international and national conferences. He has also published 4 books, 7 book chapters, and he has also awarded 2 patents. He is professional member of the different societies, including Technical Activity Chair, USNC, URSI Communication, B, Associate Editor, IEEE Antenna, Wireless and Propagation Letter, Lead Guest Editor, Special Issue on 3D Printed Antenna, IEEE AWPL norm, Associate Editor, IEEE Transaction Antenna and Propagation, Member, Directed Energy Professional Society, Editor, International Journal of Electronics and Communication, Member, Applied Computational Electromagnetic Society, Member, United States National Committee for the International Union of Radio Science, Professional Member, American Society for Engineering Education, Member, IEEE, and many more. He also achieved many awards, including Outstanding Faculty Award, San Diego University, USA, Outstanding Associate Editor, IEEE Transaction Antenna and Propagation, Young Scientist Award, IERT Commission B, Research Associate, University of Manitoba, Canada, Postdoctorate Fellowship, University of Manitoba, Canada, and many more. He was also a guest editorial board member of different journals. His research area mainly include applied electromagnetic area, which includes antenna theory, design, passive microwave device, and novel electromagnetic material, millimeters wave antenna, active phase array antenna, massive MIMO antenna, 5G communication antenna, null string antenna, feed for reflector antenna, 3D printing antenna, frequency selective surface, wireless communication, satellite communication, radar application, biomedical imaging, and many more. Professor Sharma has served as guest editor, TPC member, and reviewer for various conferences and reputed journals. Having such an intellectual personality amidst us is a great pleasure to all of us. It is our honor to be able to listen to you, sir. Thank you so much for accepting our invitation and bestowing us with your own presence. Looking forward to adding a lot of knowledge to our mind through your session. Please welcome Professor Satish Kumar Sharma, sir. Thank you, sir.
Thank you very much. Thanks for this introduction. I appreciate that you are having me, and I appreciate talking to many of you. I hope many of you are faculty members. Ajay here, it is faculty development program. And so my talk will be more of interactive nature. I do not worry if all slides are finished or not. If you see any question, right away you can ask and we'll try to answer it. I think as you have seen, they introduced me that I'm from San Diego State University. And so that's taken care of. My research lab has two measurement facilities for radiation pattern. One is far field chamber, which, do you see my second slide now? That's showing the anechoic chamber. Do you see the slide where I have an anechoic chamber picture? Can anybody tell me so I know this is showing up? Do you see my slides? On the second slide where I have moved on from the title slide. Any of you see my slide? Can you hear me? Yatindra, can you hear me?
Yes, sir.
You can hear me. Can you see my second slide?
Yes, sir.
Okay, good, good. So I have a far field chamber that operates on a Frisch transmission equation based property. You have a transmitter and you have antenna under test here. We can measure 800 megahertz to 40 gigahertz. It's a new chamber actually. Earlier I had another chamber, but which I upgraded. Then I have a mini compact range where you can do the testing until 110 gigahertz. Basically, in my lab, we have facility from 800 megahertz till 110 gigahertz, which is all the millimeter wave spectrum. And of course, we can do some testing at the lower spectrum as well as higher spectrum based on the need, and we have some resources for it. The title of the talk or the motivation here is to show you something about high gain antenna, especially because of the 5G technology, if you see. And 5G is still being deployed, not done it. And many of you maybe already have seen what's going on. If they are doing 5 gigahertz 5G, then there may be some interference with the aircrafts, right? Some countries are saying it may be okay, some are saying not. For example, I was reading in news in India, they said they are okay because they have still good separation between the altimeter frequency and the 5G frequencies. Whereas in some countries, they see the frequencies are close by and there can be an interference, especially when aircraft is landing, right, or taking off. So there is still some deployment going on, some testing going on all over the world, but that's a very upcoming technology. 5G goes all the way till Q band, even V band frequencies, right? So since you are very high in frequency spectrum, what you see that you need high gain antenna because of the propagation losses that are involved, right? So if you see that, and then you, since you have high gain antenna requirement, you look for the potential antenna solutions. One of the solution is reflector antenna, one is the phased array antenna. Certainly, why you need phased array antenna, beam steering antenna? Because it's at very high gain, beam is very narrow, right? And you are looking for point-to-point communication. Simply you are trying to connect the two beams. And at these high frequencies, since there may be lots of fading going on, right? So you want to make sure you have the beam steering to help you out, right? So therefore, beam steering is a requirement. Now, you tend to use a reflector antenna, then you have a problem of mechanical rotation. Generally, people use gimbals to rotate on its mechanical platform. However, you will see today in my talk that we, in my lab, we have done some beam steering response using a reflector antenna also. And right now we are working on one Office of Naval project, research projects, where we are trying to develop another beam steering antenna for a reflector for troposcatter communications. But the point is that if it is reflector antenna, It's very high, and again, it's good news. Less expensive, that's a good news, of course, right? But the gimbal is a problem, right? It's a weight, so bulky. So there are pros and cons, and if you have the reflector, if you have beam steering antenna, phased array antenna, then it has lots of RF electronics there. It's very power hungry. Then it's very costly. Phased arrays go in $100,000, $50,000 to million dollars, right? So it's a very costly approach, and of course it needs very costly beamforming and so many other problems. But with 5G, people are trying to design phased array antennas. Those can be low cost, right? So in my talk, I just said I have reflector antenna and phased array antenna. First, I will start discussion on reflector antenna concept, and where I will cover some information, but of course, I have 3 books on reflector antenna. Those were published in 2013 from I.E.R.T House, along with my co-authors from Ministry of Manitoba and Northrop Grumman Corporation, Sudhakar Rao. And we have 3 volumes, phased array source designs, and volume 3 about different applications that come along. Some pictures I show for the different antennas I showed you just to fill the slide. So how a reflector antenna works? Most of the reflectors work in 20 wavelength to 1000 wavelength range because the dimension is too big, and that's what translates into high directivity or gain, right? Frequency ranges from 1 gigahertz to terahertz. On several Mars missions, they are using terahertz antennas these days. So, but of course, below 1 gigahertz frequency wavelength will be too long, right? Let's say at 1 gigahertz, your free space wavelength will be 30 centimeter. And therefore, if you have even 50 wavelength, 30 into 50 becomes too big a structure. So below 1 gigahertz dimension becomes a challenge, right? So that's why they use above 1 gigahertz. Now, most of the reflectors that we use, they are parabolic in shape, right? So they follow parabola equation, and most conventional structure is a symmetric reflector. So where your feed source sits at the focal point, and you have a symmetric reflector geometry here, of course, focal length f and diameter d. So you have some f over d maintaining, and if your feed moves out, basically if your focal point moves out, then your feed gain has to go high, or rather feed pattern beam has to get narrower to illuminate the reflector surface. And if your feed pattern hits the reflector surface, it creates parallel plane waves, and that parallel plane waves is the one that offers you high directivity, right? So if you are hitting at any arbitrary surface with RF distance here, then equation is given, and again, in many textbooks you can find these equations. Now, if you are aware about physical optics, right, then the feed that illuminates the reflector surface, it induces current there, right? And that's what, if you integrate over the structure, over the surface, right, you can calculate the total radiated field. So the total radiated field can be found from that. Again, it is something connected with physical optics, but of course, geometrical optics, geometrical theory of diffraction, and so many methods people have done, and they use sometimes combination of methods to predict the reflector antenna responses. Now, since you have a feed source here, if feed source structure is big, it will be a problem because it can create blockage. Basically, signal coming from reflector will be blocked by the feed source. It affects your efficiency. So what people prefer for, especially for satellite communication application, or most of those applications, they prefer to use feed below the reflector surface or with some clearance, like the example shown here. Now here what happens that even if you have big feed source, you don't have blockage, and therefore you have some more improved response from the same reflector. Now if you have a symmetric reflector, as I said, you'll have blockage, right? And please mute some of you, because there is some sound coming from you and it is distracting me. Now, if you have a high cross polarization, in reflector, only because you have the offset reflector. Basically, if it is a symmetric reflector, right? In that case, you will have no cross polarization problem. But offset reflector, you will have cross polarization problem, because in offset reflector, you are dealing only with one half, right? And next slide, I will show you some effects, how this happens. And your feed sits at the phase center, right? What is the phase center? Phase center is the fictitious position from where your radiation starts happening, right? And this phase center can be at the aperture of the antenna, can be slightly inside, or can be outside. For example, in this quasi-log periodic dipole array, phase center can be somewhere in the middle. So basically, knowing the phase center and placing the feed phase center at the focal point offers you optimum response. Okay. Certainly, you also need to have symmetric pattern, because if you have a reflector, it's a parabolic surface. So basically, you want to illuminate either side equally. So you need symmetric reflector pattern. So not only you need low, and also you need low cross polarization in the feed pattern, because reflector is an analog integrator. Whatever comes from the feed goes out from the reflector. So if you have higher cross polarization in the feed, reflector pattern will have high cross polarization, even though it is symmetric reflector. As I told you, in case of offset reflector along the asymmetry, you will have some cross pole. But even if it is symmetric reflector and feed has a cross pole, it will show up. So it is good idea to have very low cross polarization in the feed pattern, as well as symmetric feed pattern. Plus, reflector surface should be polished. Lambda by 20 minimum to lambda by 100 order surface roughness should be there. That's people say polished surface. So those who are aware about reflector designs. And again, these are mostly used in space applications, like in India, if you have I.S.R.O. and so many places, they are using it. So if you look at the cross polar point, again, I told you symmetric reflector has no cross pole, because you can see this current here on top and this current on the back side, they are opposing, basically the cancellation of current. That's why no cross polarization in case of symmetric reflector. But in offset reflector, you are talking about only one half of the current. So there is some asymmetry and therefore some cross polarization. Another point to be aware of, the illumination of the reflector. So if you have the beam coming from feed source that is wide enough, you will spill energy, and that will show up in the back lobe. And if beam is very narrow, then, and if you have side lobe hitting the reflector surface, that side lobe will come out also from the reflector. That's also not the good news. So what you do, you maintain half edge illumination. For example, from feed patterns broadside position to one half, based on 8 dB, 10 dB, 12 dB half edge illumination. If you see here in the response from the reflector, when you have 8 dB half edge illumination, basically you are spilling some energy from the reflector that is showing up in the side lobes, compared to the case when you have 12 dB half edge illumination. When you are concentrating most of the energy on the reflector surface, you see that your side lobes are low. That means anything spilling from the reflector will come back in your side lobes or back lobes. So that's a good point to note, that you always maintain half edge illumination around 10 dB range, certainly not worse than at all, 8 dB at all, okay? And some applications do have 20 dB half edge illumination requirement, because they want to capture all the energy and they want to minimize side lobes as much as possible. Of course, when you do that, there is some trade-off in terms of gain from the main beam, but that's very little. Okay. First example I'm going to show for a reflector is about the CubeSat antenna design, especially for a 6U CubeSat light for W-band frequency. A 1U of satellite is 10 centimeter by 10 centimeter by 10 centimeter cube. So we're talking about 6U satellite, basically 6 cubes. That's what the overall satellite space. and we are designing antenna for that. Again, it is for the weather forecasting, and of course many other applications that one can use. Most of the CubeSats are in low Earth orbit, 500 kilometer to 1,000 kilometer altitude from the Earth, right? And a satellite moves based on where you are. It may be 1,000, kilometers, and then if you are on peak, then you have 500 kilometers. So it's like elliptical orbit. We are using W1 frequency because if you see the propagation loss chart here, as you see that there are some pockets where attenuation is very high, right? But if you are using the pocket here around 86 gigahertz, you can see propagation has a window. Basically, it's less loss compared to the point when you have very high loss. So we are exploiting a frequency spectrum where propagation loss is manageable, and we are trying to get back the losses through the antenna gain and the RF circuitry, that is transceivers in this case. Since it is a satellite communication application, we want right-hand circular polarization from the reflector antenna, and we want therefore feed horn to be left-hand circularly polarized, because your feed horn is illuminating a reflector. So if your field goes, it will be reverted back 180 degrees, right? So if you want right-hand CP from reflector, you want left-hand CP from the feed. And since we have very small space, 1 U, to use for the antenna, we have f over d of 0.25, which is very constrained design, basically very broad beam, and we have to maintain all the design features with 34 dB IC up again. Of course, we built and tested this antenna. So, but before that, let's talk about how we generated circular polarization. So here, at the input port, if your wave enters, one wave passes through without, like a conventional cylindrical waveguide. Let's say in this case written as E.R.T, right? Then one component of the wave passes through that goes through these air holes or circular cavities in the structure there, and therefore wave gets delayed. Like here, you're traveling more longer distance along E.R.T1 compared to E.R.T2, and that delay is the one gives you 90-degree time phase delay that is required for generating circular polarization. Of course, you also need equal amplitude, right? And that happens because of the circular waveguide. So you have equal amplitude, a 90-degree time phase, and of course that and your feed port has to be at 45 degree or 135 degree with respect to the cavities, right? Now, if you see the vector fields as time changes, 0, 90 degree, 180 degree, 270 degree, or 0 t by 4, 2 t by 4, 3 t by 4 time, you'll see that field is rotating. And that's what is the time domain nature, right? Or also time phase difference is playing the role to generate the circular polarization. Many more details about this in the journal paper I will mention later on if you want to read it. Not only that, when we started illuminating a reflector surface, that in this case it is 10 centimeter of effective aperture reflector, and we designed the feed source circular polarized as well as the strut that goes here. So any strut has to be in a way that is not contributing to any loss, right? So basically it is particular design in this case. And we not only did that, we also used some ground skirt on top of that, because that was helpful to suppress any interaction between the feed and the reflector, because f over d 0.25 is very close to the feed. Okay, so those were included in our design considerations. When you design such things, you should be aware of course, not only measuring the impedance matching or S parameter. Like here, we measured feed horn alone, feed horn plus reflector also. Make sure impedance matching is preserved and we do not have any any reflections going on. Can some of you mute your mic? So I hear some sound here. And then if you look at the axial ratio, plot here, then it is a very broad, it's a broadband, or you can say wideband design. certainly from 80 to 100 gigahertz range. But this is only at one point in the space, broadside position. That's not the best way to determine the quality of circular polarization. So what you do, you look at the contour plot of axial ratio, right? Here you have theta and phi angle simulated, and we did measure in our chamber to see that how simulation measurement behave not only at one point, rather at different phi and theta, because your circular polarization is over the whole hemisphere, right, in this case. So therefore, you can see that there is very good agreement. Many research papers, you see that they only show one point in space, and they say it's a good circular polarization. That's technically not correct, okay? We did verify at 79 gigahertz and 86 gigahertz, and to make sure feed is very good, and it qualifies for our reflector application. We measured the feed sources in our chamber in our mini compact range with the for both and we see that simulation measurement compares very well. We also looked at the 2D cut plot, and you can see slight cross poles are high because still some noise may be there in the chamber there, but then otherwise there is very good agreement. Animation is showing that there is not much spillover, and that was one of the things that in this design we maintained, because F over D was 0.25. So therefore, so basically half a illumination that we could maintain is 10.5 dB. And it is good enough. Of course, 12 dB is much better if you can, but since F/D is very constrained, so it is really, really hard problem. Those who design reflectors, they are aware about it. And then, of course, we tested the whole reflector and feed geometry like the one shown here. This is the feed source here, and this is the polished reflector surface that we built. And then we tested it. That we get our 34.36 dBIC of gain at 86 gigahertz, and of course it is much wideband. Here you can see that gain versus frequency response, as well as antenna efficiency versus frequency response. We could maintain 60% or more efficiency, and we also measured the 3D pattern of the reflector in the chamber. You can see it's nice pencil beam as we expect. Once we classified this, that everything works out. We also did some study inside the CubeSat chassis, because CubeSat chassis can contribute some scattering. So we place the reflector here, and that's based on ANSYS 7 modeling. If you have ANSYS, you have shooting bouncing ray method there. Of course, TIGRA these days already have this feature. And then this is the comparison of the result without the CubeSat chassis and with chassis, and you can see it's not much difference. Rather, some in the lower energy area, some effect because of the scattering. Otherwise, in the main beam area, no such issues. And this work was supported from my Office of Naval Research grant. And more detail about this paper you can read in IEEE Transactions, paper that appeared in March 2019. Any question on this work before I move on to something else? Please feel free to ask your question.
Yes, Anurag sir, you want to ask some question?
Please unmute. Please mute your mic.
Yes, sir. I am unmuting the mic, sir.
Sure, thank you, thank you. If no question, I will continue to the next slide, and you can ask any time. I don't know if you are aware, 3D metal printing has come these days, and has come to help in many ways compared to conventional machining, like lathe machining, where if you want to maintain 2 mils or 4 mils surface roughness, the cost is very high, right? So if you want to make low cost designs, then 3D metal printing is one way. Although it also comes at the cost of what metal alloy you're using, and also what kind of surface roughness the fab house can provide. So in this case, we used a direct metal laser sintering process through a company who we paid the money, of course, Proto Labs, and they use this approach here, and they use aluminum alloy and to as a aluminum alloy powders. They do sintering to give the structure for you. So they have 50 micrometer of surface roughness in XY axis and 125 micrometer along G axis. We did some paper that published in a journal here, IEEE Antenna Wireless Propagation Letter last year, not last year, the 2020 of April, if you want to read more information. But here we designed an axially corrugated feed horn that is wideband from 26.5 to 40 gigahertz. This full Ka band spectrum of 26 to 40 gigahertz. Again, most of the detail of the analytical detail as well as about the paper design you can read in this paper. So, but we use 3D metal printing approach. We designed also some K-band polarizers, V-band feed horns, but as you go higher in frequency beyond Ka band, the surface roughness becomes a problem, and therefore our V-band design was good for nothing. Simply, it was just simply brick. Whereas because the surface roughness made a problem, we had some circular cavity that got filled out. As you go higher in frequency, precision it becomes a challenge, right? I hope you are aware about it. So here up to K band we use, and that's what I think is a good idea. If you're using something, K band is still good technology. Up to K band frequency, still 3D metal printing is good technology. So here we have actually corrugated horn, circular waveguide. We transition into rectangular waveguide. Then we have a K connector, because at these frequencies, you cannot use conventional SMAs, right? So you have to use K connectors. And then, of course, if you see in the photograph, you'll see there is some surface roughness involved here and there. As far as impedance matching, simulation versus measurement, I will show you later on, but we also did the study called tolerance study or sensitivity analysis. So if there is some surface roughness, how impedance matching and radiation pattern will appear. So you can see matching wise, it was preserved. If you see the radiation pattern at the 26.5 and 40 gigahertz lower and upper ends, you see there is some change, but that's still very little change compared to the price saving that 3D metal technology brings to you. So it was a good approach, and we did verify before we sent for fabrication. Then after we built it, we tested in our chamber. I did the photograph of the antenna there inside the chamber, and then you see the impedance matching compares fairly well between simulation and measurement. If you look at the gain response, again, there is good comparison between simulation and measurement, except towards the end of the band, there is some disagreement, which is also, there are two factors, because the surface roughness, it may be somewhere hitting, and plus the end of the chamber spectrum. So there may be some noise floor problem. If you look at the radiation pattern for 26.5 between the phi 0, phi 90 cut, you'll see that you have the cross polarization is high, almost 10 dB compared to the simulated results. Okay, and that high is sufficient because it is coming from the surface roughness. So if it was a late machined version, then you had no such 10 dB higher cross pole, rather you are very close to the cross polarization you're seeing from the simulations. So this is the penalty you are paying, right? Because you are using a 3D metal printing. We verified also at the 33 gigahertz and 40 gigahertz edge of the band. A similar conclusion that cross poles were slightly higher, which are weaker currents compared to the simulation. Otherwise, copoles matched very well, except towards the 40 gigahertz, you can see some disagreement shows up at the far off angles. So therefore, we notice that if we can do 3D metal printing, yes, some trade-offs, but you have low cost design in this case, and of course lightweight compared to a conventional aluminum alloy or any other metal that you use. We did also design a dual circular polarized feed source, where we have a polarizer section there, both in the structure, the symmetric arrangement, and if your field enters from here, we'll see the delay. in one axis, another axis will pass through another angle. Therefore, you'll have 90-degree phase delay. And here we have 2 feed points. You can get right-hand circular polarization from here and left-hand circular polarization from the another port. And we have some shape here that you see here because that was help in making a symmetric current distribution. Especially this was done for a spherical reflector. So again, we verified this axial ratio over all theta and phi angles. We looked at the half-edge illumination of the reflector, and we looked at its scattering parameter, impedance matching, as well as gain and axial ratio. As you can see, that axial ratio is below 2 dB throughout the band of K band, which is 5G frequency. If you see, 27.5 to 28.3 gigahertz. And of course, this is also N779 or some new radio bands there that you can see. But the gain and axial ratio as well as impedance matching turned out very well, even though it was 3D metal printed. And so what we have experienced up to 30-40 gigahertz 3D metal printing is still good enough. But if you go higher in frequency, 3D metal printing fails simply. But if you do machining, it will be costly design, right? So you can save money if you use 3D metal printing, and that's one thing I wanted to convey from this presentation. Of course, we looked at the other verifiers here, but I think I just simply I want to skip slide because we started almost 30 minutes late today. Any question before I want to talk about the V-band design? Yeah, 30 minutes late. About 3D metal printing? Hearing no question. So in here we have a millimeter wave feed horn system again for dual circular polarization. Port 1, port 2, basically one is right hand CP, one is left hand CP. To generate circular polarization, we have a sectoral structure here, simply one side only. So as a wave propagates, what it sees the cavity, basically there is delay, and that delay causes the 90-degree time phase difference, while amplitude is still maintained close to equal. That means there will be, if the equal amplitude, very nice axial ratio. There is some slight variation, which in terms of dB, is almost non-dB value, not much difference. Therefore, your axial ratio is still very well maintained. And we machined it using, of course, lathe machining process, because as I told you, 3D metal printing technology did not return the good design because it filled this cavity area. So this is I don't know if you can see my laser pointer. That's where this cavity was there. So after we built it, we tested this impedance match, axial ratio, and radiation pattern in our chamber. And this paper again got published in IEEE Antenna Wireless Propagation Letters November of 2020. So if you want to read more about this paper, please do read. Okay. With that, I'm done some discussion on reflectors. I will do some discussion on phased array antennas, those who have been working on phased array antenna problems. If any question on reflector antenna, you can ask.
Yes, sir, from my side, sir.
Mm-hmm.
Sir, 3D metal printed antenna, sir. Sir, I would like to know that what are the additional features that are used to be improved using 3D?
Well, I mean, there is just the metal
Excluding the
printing
gain.
technology. It's a metal printing technology, right? So the new machines coming every day, right? There are mechanical engineers, material scientist engineers working on those areas to come back with a better surface roughness. And beyond, and if you're looking at this question from antenna point of view, then of course you have to come up with a novel design, right? Printing process is just a manufacturing process, right? How to construct it, how to make it, right? After you did the simulation design, how you build it, right? So is the 3D metal printing is the building process, but the point is that it is giving you low cost fabrication with some design trade-offs. And again, that's something new people are following to cut down the cost, right? Because everybody wants low cost design these days, right? Okay.
Yes, sir. One more question is that, sir, in aircrafts also 3D metal printed antennas are used, sir?
In aircraft, you can use, but I do not have any information because you can use it because as long as you can have temperature, pressure in control, right? And I don't think any issues with the 3D metal printing. I have not done that study myself. Neither I have seen anywhere people have done that, but I don't see a reason why it cannot be used. Okay.
Thank you, sir. Thank you, sir.
Sure. If any other question, if not, I will start this discussion on phased array antennas.
So you may proceed, sir.
Okay, so very recently we published a book on multifunctional antennas and arrays, and of course some discussion is connected with this book, and that came from IEEE Press and Wiley. Many chapters are there. Those who are researchers in this area, if you read those chapters, IEEE Explore already has some chapters there because it was supported from IEEE Press. And of course, you can buy the book here also. But then there's lots of information on high gain, multifunctional antennas, reconfigurable antennas, and all those aspects, those who are interested. And the authors are my own students, those who work with me along with myself. So what is a phased array antenna? Can anybody speak from the audience? What is phased array antenna?
Anybody from the participants?
Yes, sir. Good morning, sir.
Yes, good morning.
Yeah. In phase array antenna, basically, even if you take the linear array of the phase antenna, each excitation coefficient of each antenna, where excitation coefficient is a complex quantity, where amplitude and phase can be changed by putting the TR module to the individual antenna, and those modules are programmed depending upon the beam direction. We can change the phase value of each excitation of antenna, and so that according to the input value of the phase, beam direction can be converted as a phase array antenna. It can be it will be electronic scanning type, or else another next version is small antenna, where we can have again same phase array concept, rotate in any angle, whatever you want. In that one, signal processing algorithm is very complicated in that case, but however, more or less both come to the similar category.
Yes, good.
Is
So you are
what a simplified form one can explain the phase array antenna. Very simple form, so that a common man can understand. Easily it can be elaborated much higher level, but I don't think so. We can definitely discuss upon this one, but as of now, I feel this is more optimum thing to common man understanding.
Very nice. So a phased array antenna simply has a group of radiators, right? Like example here, when you have some radars used there, and they have rating elements, place thousands of rating elements, and by manipulating the amplitude and phase, you can steer the beam, right? Of course, as you see here, passive technique is there, distal beamforming is there, active beamforming there. Most of the time when we refer phased array antennas, we refer to electronic beam steering or active designs. If you have passive designs, and of course then you have to have some gimbal to rotate the beam. If it is distal beamforming, you take the RF coefficient and you go to distal domain, right? And then you process and you create in virtual all those beams, right? So there are different approaches these days people are talking about. And certainly most of the radar and satellite communication applications are one intended application, but these days 5G picking up, and they're trying to use these antennas on the mobile terminal side, especially in cars, vehicular applications scenario. So what happens here, if you have the input power, it comes through the power dividers, right? It keeps getting divided. Then you have some phase shifters, because phase shifter is the one that is making the beam steering to happen. So the concept is that you have a let's say first a rating element. If there is no phase shift there, that means wave is free to propagate, right? Whereas if you see the second rating element, where you have delta phi progressive phase shift, that means it is delayed by that amount. And if you keep delaying each of the rating element by the progressive phase shift delta phi, at the last element you have 7 delta phi progressive phase shift. Our delay is much more, so therefore you have a tilt there, and that's how you can steer the beam in a given direction. Simply by employing phase shifters, you are creating a delay mechanism, and that delay mechanism is pushing the beam to rotate in space, right? That's the basic concept about beam steering designs. And of course, these days the technology has gone up where you have a single RFIC that has the transceiver. Basically, it has LNH, HPH, phase shifters, amplitude control in one. So therefore, like here, the phase that I'm showing, and I have done some work, I will show some work later on, that one single chip is both transmit and receive included. And therefore, the whole size is shrunk, is shrunk, you can say, rather it's very low profile. So it's only 3 to 4 millimeter total thickness of the phase array. Otherwise, phase array tend to be very bulky, costly because of the RF component, and you have to worry about heat sink properties. So the technology has gone much, much higher, of course, due to the RFICs also. So what you need to know, first thing is that choosing the appropriate rating element. When I say right, means appropriate rating element, not right, left turn here, appropriate rating element here. That means if you want to scan the beam, how far you want to scan beam depends upon what kind of rating element you have chosen, right? So if in case you want to steer farther, choose the rating element that is broad enough, okay? Cosine to the power 1.2 to cosine to the power 1.5 order will give you most of the broad beam steering possibilities. Then you have to be aware of inter-element select spacing like dx and dy along x and y direction if it is a square or rectangular lattice in the array, right? So if the elements are too close, they will couple. And if the elements are too far, that will create a grating lobe problem. So for microstrip designs, generally 0.72 wavelength is the upper end for, because after 0.72 wavelength, you start seeing the high side lobes. And later on, they turn out to be grating lobe problem. So you cannot have far enough and you cannot have close enough. Basically, choosing the spacing dx and dy is very, very critical in your design. Then you have to be also worried about active S parameter, because what happens that once you have rating element excited, they couple. So basically current is going from one rating element to another rating element. Basically some coupling happening both on circuit side as well as in the radiated part. So therefore you have to be aware, and therefore you need to have some active S parameter in control. And of course they all factor into antenna efficiency. So these factors should be kept in mind. Another thing to keep in mind that you should be having a simpler beam farming network. A beam farming network is very complex, cost, weight, all other problems will pop up. Heat sink will become a problem, packaging will be a problem, right? Then so of course, cost is certainly important. Everybody wants low cost solution. So you have to be thinking about what kind of beam farming network to implement. And that does depend upon the technology. Like 5 years back, 10 years back, if you are designing a phase array antenna, you had no other option than to use individual LNH, HPH phase shifter, maybe analog or digital. But these days, as I said, technology has gone up for the last 2-3 years at least, where you can have the RFICs that you can, and therefore whole design can be shrunk or maybe very low profile. Of course, you need appropriate beam farming algorithm, because if you want to steer the beam in a given direction, you have to apply proper amplitude and phase, right? So if you have the total pattern here, you have to apply some progressive phase shift, and you can do through some GUI, right? You have to write some kind of algorithm, and you have to have some GUI basically that tells you, helps you in the process. And if you have a rating element, connect with a beam farming network where you have the low noise amplifier if it is received, power amplifier if transmit, phase shifters, analog or digital phase shifters. Analog phase shifters are costly, bulky sometimes because of ferrite phase shifters. But of course, you have option to choose. If you use digital phase shifters, then they have also bit, basically 4-bit, 6-bit, 8-bit, some discrete positions those are involved there. And of course, then you have to know how to control them through DIP switch, right? and then having some variable gain amplifier. And of course, eventually you want to control the array through a microcontroller. So you have to have a proper algorithm like the one picture shown here. That's one of the algorithm we wrote with a GUI to function, control the array response. So these are certain things that you should be keeping in mind. First, I will show you an example here where at W band frequency, we have the fixed beam array, as well as we did some beam steering antenna design. Once again, we looked at the situation where we have low propagation loss. Again, as you go higher in frequency, propagation loss goes up. Again, we chose this window here. And once we do that, since again 6U CubeSat, we have one surface, basically 10 centimeter by 10 centimeter, a surface where we can use the antenna there. So, and this is it's just a quick illustration how the rating element sits here. And of course, again, it is similar application I talked in the reflector example for weather radar applications. So what innovation was here that we came up with a new rating element. Again, because SATCOM application, you want circular polarization. So we chose butterfly rating elements, where you can see that we have 0 degree, 90, 180, 270. If you see the current distribution here, you can see current is rotating. Basically, when you have 0 degree versus 90 degree versus 180 degree versus 270, current rotates. And that rotation property is the one offering you 90 degree time phase difference, right? And you offers you circular polarization. The paper that appeared in IERT transactions 2020 December has very good detail in terms of analytical study, in addition to simulation and design results. So please look at for more detail. And it's a leaky wave antenna. So some leaky wave antenna theory is attached here, of course. What we did, of course, conventionally people use 16 elements in one linear fashion, but here we did a study to see how much is optimum. So we did 1 by 24, 1 by 32. You can see that if you have 1 by 32, that end elements are not getting enough current. Simply it's a waste, right? But if we did 16, lots of current was left. So we chose 1 by 24, and therefore that is that offers us very good efficiency, and that's something if you see in terms of efficiency, 1 by 16 offered 69.5 efficiency, 1 cross 24 offered 70.5% efficiency compared to 1 cross 32. So once we chose that, another thing to keep in mind, since it's a leaky wave antenna, is spacing between two rating elements, which each of them are butterfly rating element that I show in the picture here, is one wavelength, right? So that the energy can add up in far field, in phase, right? But since the elements were close by, there is some overlap of the rating element. And this was something done intentionally to make the design compact. We could do 2 wavelength spacing also. And I will show you later on some work where we did 2 wavelength spacing actually, okay? But anyway, please read the paper to get more of the information. So first we did build a fixed beam design, 8 cross 24. We also made some 32 cross 24 rating element, which can kind of give us the gain we were looking from, and of course on top of some transceiver gain here. And again here, since frequency is very high, you have to be careful of choosing the substrate material and the copper coating, copper cladding on the substrate material. So rolled edge copper is better than conventional copper cladding, if not losses are very high. And it was almost 10 mil thick substrate material, and it was outsourced and cost several, around $10,000 even to build a couple of coupons of this structure. Plus it's 1 millimeter connector because frequency is very high, so you cannot use K connector or conventional SMH. So 1 millimeter connector here that we attach it here. Then we verified the radiation pattern as well as impedance matching and axle ratio. You can see that axle ratio simulation measurement agrees very well, similar to the impedance match. One thing to keep in mind, it is a traveling wave antenna, leaky wave antenna, right? So what happens as frequency changes, beams start squinting, right? So what our bandwidth is in terms of assuming some squint tolerance, but within that, how much bandwidth is maintained, because it's a tendency of traveling wave antennas to squint the beam, okay? And here, After we did that, of course, if you see the both the simulation measurement for 86 gigahertz in Fusion of 390 plane, a nice agreement, except some disagreement you may notice here that is present from the simulation and measurement. Of course, some cross polar problem is also there, because again this is something realistic design, right? That you do, you test, and based on the, since 10 mil substrate, substrate can be bent, right? So you have to be aware. And once you did 32 cross 24, we did verify our gain, and we noticed that again it's almost a dB or something less even compared to simulations. And again, think about the fabrication tolerance at this frequency. So therefore, any small thing, even if you cannot see it from naked eye, can contribute to the surface roughness, and that can show up in the pattern that you see here as well as in the gain response. So be mindful of doing a careful fabrication, of course. We also looked at the phased response, where we design our own 4-bit phase shifter. We published in our electronics letter some about this phase shifter design using silicon germanium technology. And then we bought some LNAs and we built array. The problem happened when we made the build. That time it's a 12-layer board actually, even though it's appear very thin, it's 12-layer board. So some mirroring has happened. Mirroring means short circuit has happened. Therefore, we couldn't test it. And we are actually designing, the student graduated, and we are designing now this array to, with proper accuracy. So then we will have and test again in near future. With that, I will be talking about some RFIC-based phase designs. If you have any question on the discussion I presented, you can ask.
Any questions from the participants?
If no question, I will continue. So if you look at...
Sir, is it possible to show any physically 3D fabricated antenna? Is it possible now?
Can you again repeat your question? It's very noisy, so I cannot hear what you said.
Thank you, pardon, sir.
Can you repeat your question?
My request is, can you please show me a 3D antenna which you have been fabricated in your lab? Physically, can we see it?
Of course, this is the fabricated antenna, right? The fabricated antenna that you see here. Okay, this is fabricated antenna response simulation measurement, right?
Sir, you're not audible, sir.
You can't hear me?
Yeah, now I listen. Tell me, please.
So this is the antenna that you see here, right? On the picture here, that's a fabricated antenna. It's not simulation model. It's a photograph of the antenna that we built it.
Yeah, what I'm requesting, is it feasible to show us physically that fabricated antenna?
Or not? I'm talking from my home. It's 9 p.m. quarter to 9 p.m. right now. I don't have here, right? It is my office. It's my office.
No, sorry, sir.
Yeah.
No,
yeah, of course. I mean, it has to be in my home here, right?
Just eager because you mentioned so many workers. So just eager to know, to see physically at least glimpse of that. That's all the intention, nothing more than. I'm sorry for that. I don't know.
No, I don't have. I mean, of course, your question is valid, just that I don't have at my home, right? It will be my lab, right, at university. So anyway, yeah. So but I show photographs, right, that you should be able to see and look at the publications. We have all the details if you want to read and learn more about it, right? So the new technology that has popped up because of RFICs, right? And there are different vendors I mentioned. We published a paper last year, or rather again, I say last year, means 2020, where we have a nice detail. The project was with Army, Navy, and so many groups that we. So where we have analog devices, they sell the RFICs, and AnacuWave is another company that makes RFICs. Renaissance is another company. Now they have been bought by another company, maybe. So Mixcom and RF Core, and there are so many other companies. Those are developing RFICs these days. So the beauty of these RFICs is this: that you have in one chip, few millimeter chip, you have not only the receive path as well as the transmit paths. You have the LNAs, phase shifters, digital phase shifters, variable gain amplifiers, right? And if you do the transmit chain, you have the power amplifier and the 6-bit phase shifter and variable gain. And of course, you have an RF switch that can toggle between transmit and receive, right? So a chip is the one that is making these low profile phased array antennas these days, right? Another problem to be aware, the design. You have multi-layer boards. It's not a simple microstrip patch antenna. You have to be aware of all the feed network and going like here to the cross section. You see, we have parasitic patch and ribbon patch, and then we have so many other layers: ground, strip line, SPI control to control the beamforming network, power, as well as RF. So many things comes into play, and they are each sandwiched on top of each other, right? So that's where the problem comes, and sometimes fabrication fails. And these are still $10,000 to $15,000 fabrication at this stage. So here we show the cross-sectional image just to see that how fabrication comes back and plays the role. And also you have to do, when you're modeling the beamforming network after HFSS, you have our software, you have to go back to layout creator, right? So you can go to ITM software and you can create the layout. Like here we show the RFIC, we show the strip line and so many things, and you can see how congested the beamforming network can be, right? Again, read the paper for lots of detail about the design included here. So first example I'm showing is for 5G frequency, 27.5 to 28.35 gigahertz. Again, this is a photograph of the fabricated antenna. Of course, this is the 8x8 rating element array here, and you can see it is the chip side, the beamforming network side, with all the control side and included here. And then, of course, we also did the data throughput measurement in this example, and I will show you something about it. So we built the antenna. Of course, we tested in our chamber, and you can see the response at 26 gigahertz as well as 30 gigahertz. I can see as you go higher in frequency, your beam scan range shrinks, and that is because your inter-element spacing at same physical spacing is now more in terms of electrical wavelength, and therefore it reduces your beam steering. That's a known behavior. And we also compared, this simulation and measurement responses like the one shown here when we have 28 gigahertz simulation versus measurement, and how with respect to the criteria we chose for the rating element, how it does. And certainly you can see beam can be scanned all the way to 70-degree range, and of course based on how much gain drop you can take it. If you have 3 dB gain drop, then you have reduced beam scan range. So that's something to keep in mind. One thing to be aware that it is very hard to get the actual gain from a phased array antenna when you have RFICs, because you don't have the full control on the RFICs. The chip providers don't give that information to you. So you only measure the raw gain, simply uncalibrated gain. We did try doing with some simulation, with all the iterations, and we could see that there is some uncertainty if you want to do it, actually. You can do it, it's a very tedious process, but generally that's not so straightforward, okay?
नया वाला नहीं है ना डीएम कैलेंडर कल रीसेंट नए से शुरू हुआ
There is lots of background noise there, so some of you have to mute your mic, okay? Since it was dual polarization, we looked at plus 45 and minus 45 because dual slant polarization for base station kind of applications for 5G. For data throughput testing, of course, you have to have all the electronics in control. Since we are operating at 28 gigahertz, you have to have up converter or down converter. So on the transmit side, which in this case we have simple pyramidal horn, but we had to use a signal generator. Then we have to use up converter from 1.8 gigahertz to 28 gigahertz, and then we have some chips that call with the local oscillator they come, right? And then we could get the transmit signal coming from here, and then on the receive side, the antenna that I showed you, we connected that, and we did again. Now you have to do the reverse process. So you have to have the down conversion, basically 28 gigahertz to 1.8 gigahertz. Then you have to use proper digital modulation or the constellation construction softwares that that you need. In our example, we have 20-meter apart distance, but we have done some testing between two buildings in my university around 900 meters. And then we are doing some testing this Saturday on another phased array antenna problem, and later on you'll see some papers on those. So if you do the testing of the data throughput, certainly you have the distal modulations. You can have QAM modulation for broadside versus 30-degree steered beam, as well as 64 QAM constellation beam measured. And one thing to keep in mind is the error vector amplitude that you create. The smaller the number, better the data throughput, right? So 3.7 is better than 6.9 in this case, right? So that's something to be aware. Again, please read the paper where we have some more detail about it. Again, this is something on the communication aspect, but antenna, we have to see that it does have some data throughput capability. So we looked at both broadside as well as beam steered response. We looked at some dual circular polarization also with the same RFIC low profile phase rate concept. Once again, you can see the RFICs on this side, the radiator, the phase, the rating elements on the other side. This is photograph of the chip versus the feed network. We used nested sequential rotation to get wideband circular polarization. And if you read the paper, we have tons of more information. Of course, in the talk I cannot cover everything on one topic. So we have the verification of the radiation pattern and axial ratio, and it performed very reasonably well. And right now we are designing a phase array for NASA lunar mission 2024 actually. So where we are using K-band frequency and K-band RFICs, so we are extending the work to for that application. Any question on RFIC phase array antennas? If there is no question, I will continue. So we also looked at some beam steering response from reflectors. I don't know if you are aware that it's very hard to steer the beam from a parabolic surface. Parabolic surface, basically, if you steer the beam, by making lateral displacement, your beam quality suffers. Gain drops very rapidly. And that's not acceptable, right? So we came up with a design here where you can use a reflector surface, but it's a cylindrical reflector we are using in this case. So we designed a phased array antenna, 4x8 phased array antenna with RFICs, and that we used as a feed source. So we can get some 20-some dB of gain from a small 50-centimeter reflector. That was some Navy application in mind that time. So we came up with the thought process that how to have the phased array, and if we illuminate the reflective surface, you will see that since it is a cylinder, you will see beam steering along the cylinder axis. On the vertical side, you have parabola. So that's the only thing contributing to the gain. Along cylinder, you lose the gain property in a sense. If you have parabola, you'll have more gain. Cylindrical, you'll have less gain, right? So that's the trade-off in this case. Of course, since it's a cylinder, so you have line source, or in this case, phased array antenna, simply tilting the beam. So we looked into MATLAB programming just to make sure concept works. So when we are at the broadside and when we are steered and we see that, yeah, concept works actually, then we went ahead and then designed the phased array for that using, again, Anoki RFICs here, the radiator 4x8 and the chip on the back side with all the SPI controller, some chip information noted here, 10.5 to 16 gigahertz, but it was simply a KU band design. That KU band is covered because it's X by X and KU combined frequency band in this case. So not much fancy on the rating element, the simple stacked patch, but it provided the bandwidth, and of course we did some dual polarization because we have one polarization for transmit, one for receive. So nice, co and cross has to be there for both polarizations. That was our intended goal, of course. Since we could do it, again, it's a multi-layer board. You can see feed layer plus the rating element side, and almost 10 layer or 12 layer board, if I recall correctly, in this design. And the chip was 2.5 cross 2.5 millimeter chip. Once we built it, we tested the beam when it is at the broadside as well as when you steer it, both simulation and measurement. both for X polarization and Y polarization, because again, it's a dual polarization, one for transmit, one for receive. So we verified. Since there is RFIC, you have to also verify if there is any thermal problem. So we have infrared camera, and we measured the temperature. 58.4 degrees Celsius that you measured based on the peak power consumption that is coming from the chip, right? In this case. We illuminated before we illuminated the reflector. Actually, we did again some computational study to make sure concept works. So we went to T-graph and we created the rating elements that radiation patterns we are getting from the phase tree. I'm sorry, it's too long a day for me. I'm tired now. So when we illuminate the reflector surface, we verified the beam steering along, of course, along the axis where you have cylinder, along the vertical where you have the parabola, you have one nice beam. Okay, so we verified for both polarization, and once concept works, then we went ahead and integrated it with the reflector surface, with the phase array, and we tested in a compact range. That is with my Navy collaborators there. You can see some metal bolts there because it was a rush design at that moment, because we have to integrate it for some project deadlines. So we just found some whatever we can get from hardware store. So that's why you can see these metal bolts showing up, and we ran some simulations to see how it impacts the gain, and we verified. And you can see what you can say, metal stamped reflector. If you design surfaces, you can mold it, or you can do the metal stamping. This is metal stamping in this case here to provide the surface. And then we could measure both polarizations of the beam steering and measure the gain and the beam width information. And again, this paper came in IEEE Open Journal of Antenna Propagation. Again, it was rush design, rush deliverables, everything, because project was ending and we were in a rush to finish. But either way, we got what we expected to convey to the project. Any question on this?
Any question from the participants?
I cannot see any of the participants when I'm presenting, so you have to ask. If not, I simply am talking to
I am
black
asking,
box. Okay.
Any question from the participants? Okay, sir, I am having a question, sir, from you, sir. Sir, before going to a physical implementation, sir, which software you use to go ahead for the simulation work, sir?
So most of the time we use ANSYS HFSS. This very widely used tool, but we also have a CST Microwave Studio in my lab, as well as we have Altair FICO. But HFSS is good enough. For reflector designs, we have TIGRA GRASP, as well as ANSYS HFSS, and all other tools can do reflector analysis for you too. Okay, but they use some TOTIC, of course. Okay.
So, Advanced Design System, Keysight Advanced Design Systems, ADS.
You can do something, but I don't think that's so user friendly software. I mean, you can do some analysis, especially on the RF side, right? We are using Keysight System U ADS, but we do mostly on the RF side, power divider, filter designs. When it comes to the radiation problem, I know they created some software, but I think HFSS is much good. Okay, for that.
Yes, sir. Thank you.
Of course. This is the last work I'm presenting, but I'm really tired, so I'll be rushing up, to be honest. If you have any question, do ask me. It is something butterfly design I presented earlier, but now we made a multifunctional antenna. Actually, this was the one of the maximum downloaded paper that IEEE transaction, highlighted this month, actually, So it's a multifunctional design. Basically, one antenna takes care of multiple features: 4 polarizations, right-hand circular polarization, left-hand circular polarization, linear, basically 2 linears, as well as we can do the flexible beam steering, basically narrow beam, wide beam. We can control, because everything is connected with RFICs. They have a beam forming algorithm, so we could demonstrate all this again, all at K1 frequency. But again, since it is traveling wave antenna, so you have some squint free beam width. That's where bandwidth we are talking, where the pattern is, we are presenting in this case. Again, this came in October 2021, so if you read that paper. In this case, remember we have a spacing of 2 wavelengths. Earlier, when I presented this design, when we have 1 wavelength, the elements were almost crossing. But that was done only because design has to be shrunk. It is something what we are presenting for 5G, so space is not so constant. It's not CubeSat design. So we went ahead and spread them out. As long as you have n lambda, you will see the same response. Basically, you are repeating on the same chart, right? Same phase response. So 2 wavelength was good enough, and then of course we make 3 wavelength, losses will grow too. So no lunch free at the end, right? So you have circular polarization because of the butterfly element, 2 wavelength because so that elements are far apart. Plus we did something here. You can see this kind of element placement is called staggered arrangement. Simply, they are not kind of sitting on top as a conventional array. They're simply using the space in between. So the elements can still be packed together. So that's what is the arrangement if you see here between the 2 rating elements. There is staggered arrangement here. And also at the top and bottom, we have a dummy element, because in most of the phase arrays, if you want symmetric response, you should have some dummy elements, which we had in our array. Actually, I forgot to mention that. Then to generate 4 polarizations, if you feed from port 1, you have right-hand circular polarization. If you feed from port 2, you have left-hand circular polarization. But if you feed from both points, you will have linear X. And if you feed from both polarization, but with one port with 180-degree phase, port 1 with 10, port 2 180-degree phase, then you have linear Y polarization. Therefore, by manipulating the excitation of the port, you can see any of the 4 polarizations. Okay. And again, this work was done at K-band frequencies. This is the photograph of the fabricated antenna, of course, top view and the back view. And you can see since the connectors are K connectors and they have some physical dimensions, so they cannot be placed next to each other. So we have to make the feed lines extended such a way the feed networks can be arranged. And if they are all at the same time, they are phase matched. So they're not adding up any additional phase error in this case. So it was a very tedious process, actually, what done during COVID. So you can see that we are arranging the connectors here, in a manner that they are constructive, and they are not, of course, some losses will increase because of the extension of the line, but that's the only way we can make this design happen because of the physical dimension of the connectors. And then, of course, this is the photograph of the antenna inside the chamber, and with all the analog devices evaluation kit that we use in this case to demonstrate the response. We verified the impedance matching response, of course, for all the branches involved, and then we looked at the axle ratio response. You can see they are all meeting as the simulation measurement should correlate. You can see they are very good agreement. Again, since there is a SPI controller available from the evaluation kit, so we have to apply that amplitude and phase coefficient. So that's what we show in the block diagram, basically what makes the phase array antenna. And this chip has the 6-bit phase shift and 0.5 dB amplitude control. That's what the step that we could, make that happen. Then we verified the broadside situation for all 4 polarizations, right-hand CP, left-hand CP, and linear X and linear Y. Once we saw that there is a good agreement, and of course, good, even some cross poles are higher, because again, chamber is still a finite length chamber, right? It's not exact compact. If not, it's not a compact range. So if compact range, you have low, your noise floor level is helping you. But here we are still working at higher frequencies, so some noise floors showed up. So there is some disagreement there, you can see. But of course, we verified that for 4 polarizations, since it is a rating element, if you see here, array, along one axis, more elements, and along one axis, only 8. So beam will be asymmetric, right? That's why we have 2 beam widths, and once we did that verification, of course, we looked into the beam steering response. And not only what I show, one for right-hand CP, one for linear X, and of course the left-hand CP and linear Y were symmetric in response. Only one case we are showing up. Then we also had the flexibility to control one of the linear arrays at a time, so we can excite how many arrays we want, not out of 8, 2, 4, 6, or whatever. So if we excite only 1, beam is very broad. If you excite 2, beam is getting narrow, right? And if you excite all the rating element, beam is very narrow. Simply, it's a flexible pattern. Simply you can manipulate the coverage area, right? If you are closer, you need broad beams. You have more customers met, right? If you are far distance, you are narrowing the beam, so you can still connect. You don't lose the call. You don't lose the connectivity, right? So that's the benefit in this case. And of course, we verified the gain response. And finally, is the acknowledgement for my students, postdoctoral fellows, researchers, those who work with me and they contribute towards this project, and of course my two helpers, my dog Charlie the prince, and we have a cat, Razel the princess. Okay, so they do earn some acknowledgement here. With that, I'm done with my presentation. I think it's getting too late for me, but if you have 10-15 minute question answer, or if you want more question, I will be able to answer, of course. Don't worry. Okay, with that, I'm done with my presentation.
Any questions from the participants, please?
If any question, please let me know.
Yesterday there was a lots of queries. Now what happened? Okay, sir. I am having a question for you, sir. HFS is feasible for the terahertz frequency designing, sir?
Yes,
Antenna?
yes. Software follows Maxwell equations, right? And
Yes,
Maxwell equation has no such problem. Actually, even you can do terahertz frequency, no problem. Only thing when you have to be aware the metal start behaving as dielectric. Okay. As you go terahertz frequencies. So simulation software has no such limit, right? But be aware, if you're at optical frequency, then you have to be aware about some of those features, right? But I don't think software has a frequency limit.
I am also from the microstrip field only, sir. I have designed microstrip filter, sir, and I have used the Keysight ADS software for the simulation work, sir. Hardly, I have gone through some software workshops on HFSS, but I have seen that the ADS is faster than the HFSS.
Because ADS is not full of analysis, right? It's simply using empirical equations. So it uses the blocks and it has some assumptions, right? Yes, whereas HFSS is full of analysis. Simply it takes the structure and you have a radius and boundary. Then you discretize whole space, right? So HFSS is more accurate. It takes all finite thing, right?
But HFSS has a sir.
My one question. HFSS and CST both are software. Which software is the best, sir? Either HFSS or CST, sir.
See, that's a very good, intelligent and very good question. HFSS is finite element method based program, right? And CST is time domain based program, right? So if again, I will say that both are good. I'm not seller of any of those software, and I have both software in my lab.
Simulation time takes less in the CST, sir. Simulation time takes less in the CST, sir.
Yeah, because you have time domain, right? Once you did one frequency calculation, you can extrapolate over a large frequency, right? But in FEM, HFSS, you are doing finite element modeling. So you're discretizing whole space. So it takes more time. But from my own experience, HFSS is better. That's my experience.
That's my I3D is the very old version, I think, sir. I3D is very old version.
And of course, I3D is no more in business anyway, right? So
yes, sir.
I3D, the new G-Land software used to be in 2004, 5, right? They are not in business anymore. But ANSYS HFSS, CST, Altair FICO, these are kind of equivalent softwares. But of course, FICO is based on method of moment, and CST is based on finite difference time domain. HFSS is based on finite element method, but they all have plus and basically they are good for some kind of problem. Like method of moment is good for large problems.
One question regarding postdoc fellow, sir. One question about the postdoc fellow, sir. Suppose that I wish to do the postdoc fellow abroad in the antenna field. Which university will be the good for Indian students?
Well, again, this is all based on who can fund your research, right? Who can fund you, right? Like now I have two postdoctoral fellows. One came from I.E.R.T. Guwahati.
Under your supervision, sir?
Well, again, right now I have two. One came from I.I.T. Guwahati, one came from University of Alberta, Canada, right? So I have two postdoctoral fellows. But again, my grants are taken, right? So the point I'm answering your question, you have to contact professors, those who have funding, right? I just said my funding is taken. I have two postdoctoral fellows and their salaries, I'm paying, so my grant is packed, right? So those professors have money, they can hire you. So you should contact professors, those who have funding, and they have projects, right? That's something suits your research, right? Nobody wants to train a postdoctoral fellow, right? They want to hire a postdoctoral fellow to get the work done, not to train like a master's undergrad, right? Or PhD student. So there has to be good matching. So just keep in mind, there has to be good matching in your research and the professor who is hiring their research, right? Plus they have to have funding. Otherwise you can use some fellowship schemes that is from Government of India or some joint fellowship between USA or India, and based on which country you want to go, right? Okay.
Under your supervision, sir?
I just said right now I have my funding is taken. So I have 2 postdoctoral fellows, I'm paying salary. If I get another huge grant, maybe there will be opening. But again, selection is based on your area and my area, and do you contribute to the project, right? So, but right now I don't have any opening.
Okay, sir. Okay, thank you.
Thank you.
Sir, one more thing is one more question from my side, sir. Designing the multiple antennas, sir. We use the electronic devices also to operate it. Is it HFSA feasible for that, sir?
Actually, that's a half answer there, because in HFSS you have some circuit simulator there also. If you look at, they have several options in HFSS. So yes, HFSS actually the basic is for electromagnetic analysis, but they do have circuit analysis option there. So you can do some of those things, but not that you can model all the electronics. So there's some, if you have a scattering parameter model of a filter, let's say, right? Then you can bring that as a, in the modeling process. So you have some of those options actually. We are using right now for our NASA project actually. So there are some features, but I don't know when you say electronics, what you mean. There's so much electronics there, right? If it is only the front end, when you're talking about LNAs, HPAs, or you're talking about, then of course that is there. But we are also verifying with system U key site. Key site software system U actually, just to make sure results are accurate enough. Plus, we do hand calculation in terms of using MATLAB code just to make sure. Software can also give you wrong result, right? Garbage in, garbage out. So you have to be very aware what software is out, is offering to you. So you have to be theoretically aware.
Sir, can you emphasize on filtering antenna, sir?
Filter antennas. Well, to be honest, in my lab, we have not done any good work, rather no work actually. We have never looked into filter antenna problem because we are already loaded with reconfigurable antennas, massive MIMO, phased array antennas for last 5 years, feed reflectors, so all based on what grants I have, right? So we never worked on filter antennas, but then it's simply the concept of combining the filter and antenna together. Let's say you have an antenna operating in 2.4 gigahertz, right? Then you need a band pass filter, right? So that you have no need of separate external filter. So if you can combine the two concepts into one, that's filter antenna concept. So people have published lots of paper. Again, that's something, as I said, we don't have our own project that we did or any publications from my lab. So, but then again, there are many universities, researchers, those who are working on those problems. It's a very good problem to solve.
Yes. I had worked on that, sir, on filtering antenna, but I could not work a lot in that case. So, sir, thank you, sir. We were having any question from the participants still yet? Yet anybody wants to ask any questions from sir? Okay, sir. Then, so thank you, sir. It was a very wonderful session, sir. You have discussed the interference issues in aircraft also, and hardly we used to find the mathematical equations discussing on that. Then you have also discussed about the terahertz frequency antennas. Basically, we are only working on the gigahertz antennas. Terahertz, rarely we used to have a discussion. You have also discussed for terahertz frequency antenna also. and you have shown the applications of the terahertz frequency antenna, sir. Then you have also designed the antennas for the satellite communications. Then you have the most important thing is the 3D metal printed antenna, sir. It was a good session, 3D metal printed antenna, sir. Then you have also have done the discussions on these various softwares, that is HFSS, KeySet ADS, and CST. Maybe participants must have now they are clear through which software they have to go ahead with that. Then thank you, sir. And lastly, I would say that it was my extreme. What can I say? I am having no words to say for that. First time I am getting interacted with you, and I have gone through your papers also. I was very enthusiastic to have a discussions with you, but we are very limited with the time, sir. Maybe later on we will be have a discussions with you on the when I will be designing the antenna, and anybody from the participants also they can go ahead with, sir. Thank you, sir.